Okay, we're going to start our session now. The session is by Riccardo and Nicolas. Yes, sorry. And the title is AIGenOps, Integrating Generative AI into Platform Engineering for Regulated Software. Please.
Okay. Hello, everybody. Today we are talking about generative AI and how to introduce it into the software lifecycle, in particular in the continuous integration step. Before starting the presentation, let me introduce myself. I'm Riccardo Soro and I'm a platform engineer at Imola Informatica.
Hi, I'm Nicolas and I'm a platform engineer too. And in my free time, I am a Jenkins plugin maintainer, and sometimes I do technical reviewer for many publications. And we work for Imola Informatica. Imola Informatica is a IT consultant company, a young consultant company born in 1983. I'm also born in 1983, so I'm young too. And we are specialized in high-level activity, such as IT architecture, DevOps, platform engineering, cybersecurity, especially for finance, for bank. And we are here because the company believe in sharing knowledge, believe in networking, and especially in these events like this. And in fact, we collaborate with many universities, many organizations, and other associations. We come from Italy, especially in Imola, well known for the F1 circuit, international circuit. And it's a city located between Florence and Venice. This is important for the context where we work, because we are in Europe, and in Europe, we have to respect many laws, many norms, many standards from the European Parliament, from the Italian government, from the European Central Bank, from the Bank of Italy. And for that, we can't use AI in a free way. We have to respect the AI Act that say what can you do in the business context with artificial intelligence. We have to create a resilient system in according to the Digital Operational Resilience Act, DORA, another DORA. And we also we are obligated to create accessibility application, because everyone can use your application, especially blind people. And we can send the data outside the Europe. All the data have to remain in Europe, especially the personal data. And for that, me and Riccardo, a long time ago, we started discussing on how to integrate generative AI in the platform engineering, respecting all that, all the context, because in the bank, especially the bank, is a complex regulated context. And for who don't know, for regulated context is intended all that environment that have to respect standardization, certification, for example, medical, finance, aerospace, automotive, and so on. And for this in mind, we have tried to discuss how to introduce generative AI in the CI process, especially for generate unit test and fixing vulnerability and bugs. But we don't want to create something, a daydream imposed from the ivory tower. We want to create something that is achievable in the real world, that is useful for developer. Because if we generate 600 unit tests for a API REST and send it to the developer to check the response of the developer is something like this. No, and it's right, it's true. We have to keep in mind the developer experience. We have to think about the developer, and we have to do something that make the work of the developer easy. We don't want to be another source of problem, another source of work. We have to think about the developer experience. For that, we start to create a list of requirements to do that. And what we have in mind is that we have to think about the performance of the process. We have to think about the cost of that. And we have to take in mind the security also for the law and the quantity of data we can generate and a zero trust approach. We have a man in the middle to check what we have to do and start to think about this process. But if we start in an old style DevOps cycle, build, test, deploy, monitoring, etc., and simply introduce a step of generative AI, the only thing that we have is that many application manager call us and say that the pipeline is slow, it's too late, it's all about the DevOps, and it's not what we want. Instead, we try to think about the performance, not the velocity of generative AI, but the performance of the platform, the entire process. And we have to avoid the degradation of the performance of everything introducing generative AI. So we start in a modern approach, inner loop, outer loop, and we introduce a generative loop that retrieve data and generate data triggered by the outer loop, and when it's finished, a pull request versus the inner loop. But we don't live in a world of infinite resources. We have to save money, we have to save computational resources, because bank never has money, and we have to try to check a solution for that. And the first one is sharing the resources between the normal platform, the normal CI, and the data generation. And for that, the normal platform running during the business day, during the business hour, instead the platform, the generative loop, working on out of the business hour, in the night or in the weekend. And then we have to optimize the generation, because in our bank where we work, we have 3,000 components that is managed by the platform. And use the generative AI on 3,000 components is more difficult. So if we have an application portfolio like this, where we have an application A with 95% of code coverage, 10 code smell, and 1 low vulnerability, an application B with 80% of code coverage, 100 code smell, 10 minimum bug, or 2 low vulnerability, and an application C with 60% of code coverage, 1,000 code smell, 3 high bug, 7 medium bug, 1 high vulnerability, and 5 medium vulnerability, it not makes sense investing resources in the application A to increase code coverage from 95 to 96%. And I don't have any advantage for this. The same thing is growing the code coverage from the application B from 80 to 85, or solving some code smell or low vulnerability. What I have to do is focusing on the application C, on the worst application, and working on only the worst applications. To do that, I obtain that iteration by iteration. I don't have the 100% of all of the perfection. I don't care for that, but I arrive at the minimum quality of the entire application, because we have also legacy application written 10 years ago that don't touch so often, and something else.
Okay. So in previous slides, we saw when and where apply generative AI. Now we'll see how to do that. So Nicolas said that the generation of data must be async to the continuous integration. So in some way, we need to store the CI that are done during the day. And during the night, we have to start a process, a job on a system that can handle this type of workload, like Jenkins or Tekton, GitLab. And this job needs to retrieve information from a Git repository. So you need to do a Git clone or Git checkout and download the code base. After that, the system can interact with a tool that can give it some metrics about the project. SonarCube is good for that because it gives us metrics about coverage and quality issue. So now the system have everything that you need to call a model. And in that interaction, the system, the context that the system give to the model is composed of the code that had to be fixed and metrics about that. The model return a solution that can be a path to a file, for example, or a new file if we want to create a new unit test, for example. After that, the system in some way had to check the output. It's not easy, but there's something that we can do to test the output of an LLM. And after that, if everything is okay, the system can push the changes to the remote repository. Well, this is an example, an architecture system. That's not the only one. Today, models are powerful and they can interact with the environment and system using MCP server or skill. We tried also this solution, but in that context, it was not very good because, well, it's a bit expensive, and also sometimes the model don't follow the instruction, and they sometimes looped into the MCP server call. So we prefer the other solution. It's more, it's a solution with less entropy, we can say it. So now we have our architecture. We need to select a model. There are a lot of models like ChatGPT, Gemini, Claude. They are powerful. They are very good, but we are in the European Union, so we can't use them. We need to use a self-hostable model. A self-hostable model is a model that you can take and put in your machine, and is compliance with law, because data remain inside the organization. A self-hostable model has also the advantage to you can customize the parameter inside it, so you can control the generation of data. And that's very important, but before we talk about parameters, let's spend just a few words about models that are self-hostable, like DevSal, Qwen3, and Gemma, and how LLM works. So an LLM is based on transformer architecture, and the output is probabilities. And so we can see it like a function that take a vector of words as input, and it generates as output a word taken it from a pool of likely word ordered by probability. Well, let's see an example. For example, if we ask what fruit can I put in the fruit salad, the model generates the answer token by token. And for example, in this lot, after put, the pool of token are this one, and the model chose one of them randomly. So it's not a deterministic by default. Okay, now we can talk about hyperparameters like top key. Top key set the size of the pool. So if we set it to 5, for example, the pool size is of 5 elements. In the second example, we can see that if we set the k value to 3, so the pool is composed on only 3 elements. So a low key value means a more deterministic model. Another hyperparameter is top p. Top p works like a top key, but with probability instead of units. So, for example, if we set the p value to 2, so only the first 3 tokens can be taken, because the sum of the probability just exceed the p value. In the second example, we can see that if we set it to 0.8, for example, just only the first token can be taken. So a low top P means a deterministic, more deterministic model. Okay, just a precisation, value are just for example, are not real. They depend on the model, so it's just for example. The last type of parameter is temperature. Temperature is a multiplier that the model apply to the probability of the tokens. So a low temperature means a positive multiplier. So the gap between probabilities increase, and so the model is more deterministic. With a high temperature on the other side, the multiplier is negative, so the gap between probability decreases, so we have a flat distribution of probability, so the model is more random. But why are we talking about parameters? Because we want to find a way to freeze an LLM, to make it deterministic. And that is very important because if we want to test it, for example, we want to find, try different prompt. If we have a deterministic LLM, we can change prompt without entropy. And yeah, we can do that if with a self-hostable model. We have to set the hyperparameter that we have seen in the previous slide. We also have to fix the random seed in the code. We have to keep the same infrastructure over time. We have to disable the optimization. But if we do all the things, we can have our deterministic LLM. So that's a way to test it in a reproducible way. And that's a way also to try different model, because we want to find the cheapest one that is able to solve our problem. And here an example, there is a link to a repository, and you can find a project with a LLM, and you can run it on your machine. Well, so now that we have a deterministic LLM, we can work on prompt and test it. For our problem, the prompt is very simple. We just ask to solve a issue, for example, and Sonar give us the part of code that break the rule, and also how to fix it. So we have just to take everything and ask to the model to solve it. And well, but we work with a small model, so a different word can change the quality of the response. On the right part of the screen, you can see that that's a paper that say that for some model, some words increase the quality. For example, it's a bit strange, but for one old model, if you add in the prompt, take a deep breath and work on the problem step by step, it increases the quality of the response. So we want to say that you have to test very time the prompt and find the best combination of words that improve the quality of the response. So now that we have also the prompt, we can start generating data.
Yes, but as we say before, it's not a good choice to generate a large quantity of data. We have to limit the quantity of data, and the data we generate have to be of high quality. To do that, we don't only focusing on the worst application, but focusing on the worst things of the worst application. So instead of trying to resolve all vulnerability or arrive to the perfection of the code coverage, we are concentrating only in the less coverage class and generating only 4-5 unit tests for that class. And in the same way, we don't check to solve all the bug, all the vulnerability, but we're focusing on the worst vulnerability. And the worst vulnerability is not the one with the high level of severity. Is the one with the high level of exploitability of the vulnerability. Because if I have a backend application, air-gapped, not exposed, with an high level vulnerability, and a front end application with a low vulnerability but exposed is better concentrating on the low vulnerabilities than can create a more damage with in an easy way for the attacker. Doing that, we create only small pull requests with only 4 or 5 unit tests or less code to solve the vulnerability. Doing that, we have to check that the unit test is of high quality, that work for us. And to do that, we have to respect some requirement. The first is that the project must compile. If I generate a unit test and the project doesn't compile, we have a big problem. The same if the test don't pass, because I have the assumption that the code is right. We generate the unit test, the test don't pass, there is a problem in the test. The coverage must increase because it's no, there are a problem in where the test pass. And the unit test must be of high quality. This might make sense for the project. And to do that, what's in my guardrails, how I check that. And the idea is to use the mutation test. The mutation test is a simply check that if I change the code, the test must fail. Because if I make a unit test and I change, for example, a if statement, and the test don't fail, there is a problem with the test. What test? The test. So, for example, generating the test, change the if statement, check the test don't pass, react all the generated code. In the same way, I have to check if the fix of the vulnerability is of higher quality. And in the same way, we have a list of requirements. As seen before, the project must compile, because if I solve the issue, but the project doesn't work, it's not okay. The test must pass, because I don't have to change the behavior of my application. I have only to fix the vulnerability. And I don't have to decrease the code coverage. If the code coverage decrease, I can recreate new unit test to do that. And the generated code must solve that problem. How can check that? I resubmit my generated code to Sonar Cube, to the MySasta tool, and check the vulnerability. If the vulnerability is disappear, is okay, but in the same way, I don't have to introduce another vulnerability, another problem. So I have to check that the number is less. A simple flowchart of what we say is the same. It starts the job check out the project from the repository, from Git, retrieve the data from SonarCube or the SAST tool, and start to generating the unit test for that class we have found. And then check the various requirements. If check if the model is formatly corrected, if check is the project compiled, then check that the tests are passed, check the mutation test, and check the code coverage is increased. If all the check is okay, we propose the pull request to the developer. If also one of that fail, we react all the code and restart the process. But we don't have the luxury to accept without checking all the code is generated from their AI. Because we work for the bank, we don't know all the specific project what to do. So we need a man in the middle, a developer that know the domain, that know the applications, that know the code, that know everything, that make a check that the pull request is okay and accept that code.
Okay, now a little demo. It's not live because it takes a lot of time because I run the model on my PC, so it's a bit slow. Okay, so for the demo, we created a small Java application, just 3 classes, with some Cosmel, something that we know that Sonar will signalize as issue. And we didn't write some unit tests, so the coverage is low. And the idea is to use some job to solve part of the situation. Here there is two jobs, one for the coverage and one for the quality issue. And okay, here there is the list of classes, and this one have 0% of coverage, so we want to fix it. And on the left part, there is the model, so we will see the output. And it takes a lot of time, so we skipped this part. And okay, so the model, everything was okay, so the coverage increases. And the system open also a merge request. Okay, with the new unit test. Now we can do the same thing for an issue for one of them. And the job need the ID of the issue. So now I'm looking for it. Okay. And well, that's the same, a different job, but it work similar to the other. So it take as input the ID of the issue, and it call to the model and test the output, and if everything is okay, it creates the merge request. So okay, we can see now that yeah, the issues decreases, and there is the new merge request. Okay, the merge request simply contains the patch to the file. Okay, so we tried the system with different models, small models, and well, we found that, for example, Mistral 8 per 22B, well, is very big, but the result is very similar to Llama Code 34B. And we tested also a very small model like Mistral 7B. And so we have some consideration. For example, that the generation of fix of issues is more complex than to generate a unit test. So our idea is to see the problem as two different problems and use two different models to solve them, because we want to use the cheaper model that is able to solve the problem, because we want to keep the cost as low as possible. The other thing is that specialization is very important. So instead of using a big model, you can use a specialized one that is working very well. So if you have a task, maybe you have to look for a model that is specialized in that task. Maybe it doesn't exist, but if there is a good idea to use one of them. Another consideration is that Mistral 7B is very, very small. It can be run in every computer, but it is able to solve some problem like a generation of unit test. So maybe you can consider to use it instead of big one if you have a lot of infrastructure. And well, what next? We did the same experiment also with open source project, the CLI of Prometheus. Sonar found 800 issues, small issues, not critical one, but the system was able to solve 500 of them, so nice score, considering that we are using a very small model. Another point is to evolve the algorithm of selection of application and issues inside the application to be solved. Maybe you want to try to train a model to select it. Another point is to test the agentic approach. We did some experiments some times ago, but small models were not able to work well with an agentic approach. But maybe today it's different, so we will try it. And we want also to integrate with other tool, so like dependency track or checkmarks, so with a focus on security. And the last point is that organization usually have some custom framework and model cannot know the framework because it's an homemade. So we need to find a way to transfer the learner of the custom framework to the model. We did it with a big model. With a small one, it's a bit difficult, and we are working on it. And well, that's all. And thank you very much for your attention. If you have any question, we are here.
Thank you, both of you. Anyone have any questions for them? All right. Okay.